Hello my dear friends, welcome to my YouTube channel. This is our YouTube channel ADC Max. In this class, the second or higher order, so there is a second section, the very important section in the partial differential equation, because previously we have seen that how to frame the partial differential equation, how to construct by eliminating the arbitrary constants or by eliminating the arbitrary functions. Later on we start with the solutions, how to solve. But the solution of partial differential equation can be classified by their order. The first order partial differential equation, there are some kind of assumptions, some way of solution techniques. But for second or higher order homogeneous partial differential equation with constant coefficients, it has some different step, because in the homogeneous equations they are maintained as homogeneity first of all, and the coefficients are constant, maybe second or maybe higher orders. So in this topic we are not going to discuss the usual way, that means that to get the complementary function or complete integral or the singular integral or the general integral. No, nothing like that, because those parts comes only in case of the first order partial differential equation. That too, it is in terms of some arbitrary constants. But this time I focus only on the particular integral. So particular integral, what is meant by particular integral? It is nothing but when we assign the particular values to the constant. But this time it is not a constant. There are two operators, namely d and d dash. Because as we know that our ultimate aim is to get the z. What is z? Z be the function of x and y. Right, sir? Isn't it? So when we differentiate with respect to x, I get the first partial derivative, that is d. When I differentiate with respect to y, I am getting the second operator d dash. So there are two operators, d and d dash. So I want to replace these two operators by some particular values, so which will generate automatically the particular integrals. Got it? Now d stands for differentiating with respect to x. What about 1 by d stands for integrating with respect to x. In the similar manner, d dash stands for the differentiation of y, and 1 by d dash stands the integration of y. So correct? Now let us see that entirely in this topic our ultimate aim is to get the complete solution z, it consisting of two parts, namely complementary function plus particular integral. So how to get the complementary function? Suppose the given PDE is of the format is a function phi of d comma d dash, because I told you that this involves some operators d and d dash, partial derivatives like the d and d dash. So the left hand side is phi of d comma d dash into z is equal to f of x comma y. So from the left hand side I can find the complementary function. When I substitute the particular values to the operators d and d dash with the help of the right hand side function f of x comma y, I am getting the particular integral. So left hand side will give the complementary function, right hand side function will give the particular integral. So that's why finally we can combine together, we get the required complete solution. Now how to get the complementary function? Let's see that. A simple technique. When we need the complementary function, we assume that right hand side is 0. At the same time, replace the operator d by some parameter m and d dash by the constant 1. D by m, d dash by 1. Then the given left hand side becomes phi of m into z equal to 0. So that means that either phi of m equal to 0 or z equal to 0. But z equal to 0 means that's a trivial case. Once z equal to 0 means there is no partial differential equation, not at all possible. So that's why we avoid z equal to 0 case. So which one is 0 then? Phi of m is equal to 0. So this is a polynomial in terms of m. If I solve the polynomial, this depends upon the order. If it's second order, I get 2 roots. If it's a third order, I am getting 3 roots. So when we solving this equation, I am getting the roots, namely m1, m2, m3, etc. etc. This depends upon the order. Suppose the order is 2 means I am getting the second degree polynomial. There is a quadratic equation. I get 2 roots. Suppose there are the given partial differential equation is third order, then I am getting the cubic polynomial. So there are 3 roots exist. Suppose it's fourth order, I get the fourth degree equation. When I solve the fourth degree equation, I am getting the 4 roots. So it is the general rule. So after getting the roots, depends upon the nature of the roots, I may frame, I may define the complementary function. This time I would like to choose the arbitrary function. So the complementary function, this time I would like to use some arbitrary functions, that is f of y plus mx. What is y plus mx equal to c? Is called a straight line equation, linear. Y equal to mx plus c, or c is equal to y minus mx. So y plus or minus mx. So this is the constant. So this time I am going to define the complementary function is a function of constant. Is a function of constant. So for each root I am going to define one function. So the first root m1, my complementary function is the format f1 of y plus m1x. For the second root, f2 of y plus f2x. The third root, f3 of y plus f3x. So continue like that. Any number of equations or any number of roots are available, depends upon the order you may write. Now, suppose if I am having the roots are equal roots, what we will do? Suppose m1, m2, m3 are real roots or complex roots, doesn't matter. If they are distinct, this is the idea. If they are equal, for example, m1 and m2 are equal. m1 and m2 are equal to some theta. Then what is the corresponding complementary function? So m1, m2 are theta. So we can replace this by f1 of y plus theta x. This is equal to f2 of y plus theta x. So there is no third root. So we can stop up to this. But these two are repeated. They are equal. Then when we multiply one x with any one of the function, either first function or the second function. Once I repeat that, the roots are repeated twice. We multiply 1x with any one of the function. Suppose there are 3 roots, m1, m2 is equal to m3 is equal to some lambda. There are 3 roots, all the 3 roots are equal. Then the corresponding complementary function is f1 of lambda x plus f2 of lambda x plus f3 of lambda x, y plus lambda x. So for each root, I introduce the function f1, f2, f3. But in this case, they are equal, they are repeated. So for the repeated case, how many times repeated here? 3 times. So you multiply the first one by x to the power 0. What's x power 0? 1. So we want to multiply. The second one I multiply by x to the power 1, that is x. The third one I multiply by x power 2. So the roots are repeated 3 times. We multiply 1x x square. The roots are repeated twice. I multiply 1x. 1 with the first function, x with the second function. So this is the general procedure to find the complementary function. Okay. The next video I am going to discuss how to get the particular integral. Okay. Thank you.